Okay, so we'll start. So we were like looking into this greedy graph algorithms, and we had already talked about two algorithms, both trying to compute the minimum spanning tree in two different ways. And today, as I said, we will start off with the Dijkstra shortest path finding algorithm. So this is like a very simple modification of the Prim's algorithm that we have already known. And like as you will see, the data structures, etc., are very, very similar. So only difference is that this works on a directed graph, which is also weighted. Okay, and we want to find the shortest path from a single source. So the one that we learned earlier in our DP chapter was all pair shortest path. Okay, and this is the single source shortest path. So now here the idea is very, very similar to the Prim's algorithm. Okay. So again, we will initialize a set Y that contains the vertex from whom the shortest path needs to be computed. Is the screen visible to everyone?
Yes, sir.
Yeah, so somebody is asking, I'm not sure why, but I have shared the screen. And I guess I'm also audible, right? Because that's why you could respond. Okay.
Yes, sir.
Yeah. So, yeah, Ronak, maybe there is some network issue on your side. Yeah. So now let's say without any loss of generality, again, we start with V1. Okay. And we want to determine the shortest paths from every other node to V1 or from V1 to every other node. Okay. Once again, our F is the set of edges on the shortest path. Okay, and we start off with an empty set. Now we add the nearest vertex of V1 to Y and add the edge to F. Note that here it's a directed edge. Okay, so we are adding the edge V1V to F and the nearest vertex to V1, nearest vertex of V1 to Y. Okay, let's call that vertex V. And definitely this is the shortest path from V1 to V. Okay, now again we will maintain the set V minus Y like earlier. Okay, so now we try to do something as follows. We check the paths from V1 to the vertices in V minus Y that has Y. Okay, that has the vertices in Y as intermediates only. Vertices in Y as intermediates only. Okay. A shortest path among these paths will be the desired shortest path. Okay. So the vertex at the end of such a path is added to Y, very similar to the Prim's approach, is added to Y, and the edge that touches that vertex with the set F is added to F. Okay. So this is how you construct the shortest path, okay, from the source V1. So V1 is like one example. Without any loss of generality, we will assume V1 to be our example vertex. Yes?
Sir, could you explain that last part? So the edge which we are adding.
I will explain. I'll explain. Yeah, I'll explain. As soon as we see an example, it will be clear to you.
Sir, can you scroll up a bit?
Yeah. This much is fine?
Okay, sir.
Let me know when it's done.
Yes, sir. Yes.
Okay. So let us take an example and try to clarify your doubt.
Sir, sir, why are you making a directed graph?
As I say, Dijkstra's algorithm works on directed graph. All this time we are talking about directed graphs only, right? So Dijkstra's algorithm works on, so as we have defined here also, all the edges are directed edges. Okay. So Dijkstra's algorithm is for, I think I told you last day also, this is for a directed weighted graph. We are finding shortest path in a directed weighted graph. And that's a single source shortest path. Okay.
So what is the direction from V5 to V4?
V5 to V4, yes. V5 to V4 is in the direction of V4. Okay. So now we start with y equals v1. So we are wanting to find out the shortest path of v1 to every other nodes in the graph. Okay. So naturally, the vertex that is nearest to v1 is, in this case,
V5.
v5 is the nearest vertex. So we add in y and our new graph becomes this is taken, this is taken. Now, as I said, that after this, we will have to compute the shortest path with these two vertices as intermediates. But V1 cannot be an intermediate in its own path. So that means effectively shortest path with V5 as the intermediate. This intermediate idea is very similar to the DP approach that we saw earlier. So V5 gets added. What is the next? What should be the next vertex?
V4.
Okay. V1, V5, V4. So initially we have included the edge, this particular edge, V1, V5 into the set F. Now, after inclusion of V4, what are we going to include in the F set?
V5, V4.
V5, V4. Okay. And do you see what is the meaning of touching now? This vertex touches F, okay, using this particular edge, right? So that's why this edge is added. This is what is the meaning of touching. Is that clear to you?
Sir, can you say that again?
Yeah. So now your candidate vertex to be included is V4,
Yes.
right? And which edge is touching V4 with the set F? F has vertices with edges in between them. Okay.
Yes, sir.
Which edge is touching it? This particular edge, right?
Sir, from
Is
V1 to
touching
V4, it is
V4?
also touching. Sir, I didn't
No,
get.
but it has to be the minimum most.
Yeah, minimum one is this V5 to V4.
Yeah, so that's what, right? It is the minimum weight edge that is touching. It
Sir,
has
I
to be the
didn't get
minimum.
defining touching.
Huh?
Yeah. I didn't get how you are defining touching a vertex.
So vertex V4, okay? Vertex V4 is, so what is F now?
V1, V5
Before
and
this, F is V1, V5. Okay? V1, V5. And now you are including V4 into Y. Right? Which is the minimum weight edge that is touching V4 with F. Which edge is touching any one of these vertices of minimum weight? That's why we are not talking of direction here. We are only talking of touching. So V4 is the vertex being included in Y. And if I consider V1, V5 to be the already included edge in F, then I look for which vertex among this is connected to V4 with the minimum edge weight. Okay, and that edge, the edge that connects any one of this with V4 with the minimum edge weight, that gets added to F, and F now becomes V1, V5 and V5, V4. This is the meaning of touching.
So we add V4 after checking the edge, right? Then why do you
Yes.
check the edge again after adding it to I?
No, come again, come again.
I mean, we add V4 to Y after checking the edge V5, V4.
No, we are checking shortest path. Shortest path from V1 to everyone using only the intermediate vertices V1 and V5.
Oh, I see. Okay, understand.
Here you are checking shortest paths every time.
So, sir, this will mean that we are getting shortest paths to V4.
You are getting shortest paths from V1 to V4. See,
But sir,
every time
if
you are
you-
computing the shortest path
Sir,
with
if we have
intermediate vertex. With
yes, sir, if we have
intermediate
V1 to V5 that has weight 3 and V1 to V4 that has weight 4.
Yes. So
And
then
then
V1 to V4 will be the first vertex. V4 will be the first candidate vertex to be added if that is the lowest cost vertex.
no, sir, V1 to V5 is 3 and V1 to V4 is 4.
V1 to V5 is 3 and
V1 to V4 is 4.
V1 to V4 is 4. So what?
And V5 to
So
V4 is 4.
then he will arbitrate. We will have such arbitration conditions. Please wait. We will have such arbitration conditions or like lesser shortest path conditions. We will have soon. We will see what will happen. So every time here you are computing the shortest path. So V4 is selected because it is the shortest path from V1 using only the vertices in the set V1, V5, but V1 cannot be used. Only V5 will be the intermediate vertex. Okay, V5 is the intermediate vertex. So using V5 as the intermediate vertex, what other vertices can you include which builds a shortest path? That is the question that you are asking. Let's proceed and we will be more clear about this. You will see the fun happening just now. So at this point, you have the intermediate vertices as V1, V4, and V5. Okay. Now, what is the next candidate vertex which builds the shortest path from V1?
V4, V2.
Huh?
V4 to V2.
Sir, from V1,
V4 to V2. From
V1 to
V1, V1 is the source.
V1 to V3.
Very good. So you see, this is where the question of arbitration was coming, because this edge is of weight 4. Okay. And if you had taken V4 to V2, that would be 1 plus 1, 2 plus 3, 5. So the next candidate vertex should be V3. With intermediates as V4 and V5, the next candidate vertex to be included should be V3 and not V2. Because there is a direct edge from V1 to V3, which has a smaller weight than the sum of the edge weights on the path from V1 to V2. Right? So one path is 7, that is also large. The other one, which could be a potential path, that is 1 plus 1, 2 plus 3, 5, which is also larger than the path from V1 to V3. So therefore, in this state, V3 is included. Okay. And not V2. And then finally, in the last stage, you include V2 with the edge V3 to V2.
Sir, why we are including V3 to V2? Why not V4 to V2?
V4 to V2, that will have a larger cost now.
So it has 5 and V3 to
That
V2
also
has
has 5.
Yes, sir. Both are.
So any one of them is taken. Any one of them is taken. Here is an arbitration.
No, sir. The second one has 6.
Wait, let us calculate. Wait, let me finish drawing. Is there anything left? I think it's all done, right? So now at this point, we take all the edges, sorry, all the nodes. And the shortest path from V1 is. Agreed?
Yes, sir.
Cannot be shorter than this. So now you see, from this single source, you have found out the shortest path to all the other vertices in the graph. Okay. So this is what the Dijkstra algorithm does. And if you think carefully, you can very easily modify the Prim's algorithm to work for the directed weighted graph and compute the single source shortest path.
Sir, why
We will
is the
see
graph
how.
needed to be directed? Sir,
Why is the graph needed to be directed?
yes, sir, why can't we do for undirected graphs?
You can always do it for the undirected graph, but the Dijkstra's algorithm was traditionally built for the directed graph. Okay. The Dijkstra's algorithm was traditionally built for the directed graph. Okay, tell me, like if you have a spanning tree, if you have a minimum spanning tree of a graph, can you compute? So that's always for an undirected graph, right? If you have the minimum spanning tree, can you compute the shortest paths between, like say, starting from a particular node? In an undirected graph? No answer. Okay, so think about it. That's a homework. So here, for the Dijkstra algorithm, remember, there is this word single source. So whenever there is this notion of source, okay, this means there is a direction indicated.
So about the spanning tree, not always give the short.
Yes, very good, very good. Because
So I can just create a counter example.
yes, you can give a counter example. Very good, very, very good. So because this is a greedy approach and the optimality condition, the optimal substructure condition rather, let us say, does not hold here. So therefore, if you have a MST, you cannot always say that you can get the shortest path between any pair of nodes. Had it been the case that this spanning tree, the minimum spanning tree that we developed, obeyed the optimal substructure idea that we discussed in the dynamic programming lectures, then that shortest path argument that I have put forward would have been correct. But this is not correct in general for any MST. Okay, it's a very good observation. Okay, so here for the Dijkstra, why do we take a directed graph? Because when Dijkstra actually developed this algorithm, he had directed graphs in his mind. He had some applications in his mind. That's why he called it a single source. So when there is a source, there are multiple targets. Okay, there is a source target. As soon as there is a source target notion, it typically indicates a directed graph. Okay, and here there is a single source and all the other vertices in the graph are potential targets. That's why we typically develop the Dijkstra algorithm for the, or we typically refer to the Dijkstra algorithm as an algorithm for directed graphs.
Sir,
Yes.
sir, do we always get a spanning tree after using this algorithm?
Spanning tree for?
I mean, for this graph, sir.
We are not computing spanning tree at all here. We are computing shortest path.
Yes, sir. But after using this algorithm, like you have what created in the red diagram, red pen. So it seems like a spanning tree.
No, it's not a spanning tree. Here we are taking care of the shortest path. It's very similar to the Prim's algorithm, but here we are computing the length of the whole path. There
So
we
sir,
were
it is a
greedily
spanning
adding
tree,
the,
but not the minimum one.
may not be the minimum one. See, the spanning tree is, do not confuse these things. Spanning tree is only meant for undirected graphs. Okay, spanning tree comes in the context of undirected graphs only. Keep this in mind. So here again, we will maintain two data structures. So again, let me remind you, do not confuse between spanning tree, spanning tree. Okay, so now just like nearest and distance that we kept in prims, here we will keep two such data structures, touch I and length I. What is touch I? This is the index of the vertex V in Y such that the edge VVI is the last edge on the current shortest path from V1 to Vi using only vertices present in Y. Length I is the length of the current shortest path from V1 to Vi using only the vertices present in Y as intermediates.
Sir, can you please scroll a bit? Yes.
Signal when done.
Yes, sir, done.
Okay. So now with these two data structures, we will try to write the Dijkstra algorithm.
Sir,
Sir, you are writing vertically down.
sir, it is tilted.
Sir, your screen is not rotated.
Oh, Wait. Now is it visible?
Sir, it is
So it is
visible but
visible,
tilted.
but nothing but factored into.
Okay. Actually, I tilted it for writing, for having more space. Okay, let me try to write it as it is. Now fine? Now is it fine?
So did you write
Sir,
anything?
please try to write.
Is this now visible? This one, the one that I'm showing?
Yes.
Length
Yes, sir,
height,
the length
touch
is
height.
visible.
Yes, sir. It
Okay.
was visible before also, sir. But the thing which you're writing is coming downwards.
Yeah,
Like
because I think because of the pad, because of the trickiness of the pad. Anyway, I'm trying to write it. So I wanted to use it in the portrait format and it tried to play its own tricks. Now also tilted.
No, sir.
No, sir, it's fine.
No, sir, it's fine.
Okay. So W is the same weighted adjacency matrix like we defined earlier for the Prim's algorithm. Only here, it will also have the directional notion. Same as earlier. Then what? Indexed by minimum shortest path, length, index has come in linear.
The touch of veneer.
Very good. Touch of veneer. To
Veneer.
veneer. Right? The touch of veneer to veneer. That edge will be added.
So could you explain this again? The touch of veneer and
So this is Do you remember the Prim's algorithm? Do you
Yes, sir.
remember? Were you there in the class?
Yes, sir.
Yeah. So what did we do there? What was the idea there? This was, in that case, this was nearest of veneer.
Yes, sir. The nearest which was connecting to the veneer.
So similarly here also, that is contained in touch of veneer. So touch is the set of vertices which is containing what?
Is it nearest to veneer?
That is like the nearest of veneer. So if you recall the definition of touch, so index of the vertex V in Y such that this is the last edge on the current shortest path.
Okay, sir. Got it.
So basically Y has the touch of veneer and V minus Y is the veneer. From here, veneer will be now going into Y after this step. Now here there is a slight modification. You are now computing shortest paths and keeping track of shortest paths. So how is the length updated?
So length I plus W of
Length I,
length of touch veneer.
touch veneer. Who is getting added to I?
Veneer.
Length of veneer plus
H from
plus
veneer to
W of
veneer, comma I.
veneer I. This should be less than
Length of I.
the direct length I. This was not happening for that example case where directly V3, what was that node? V1, V3 got added. So this path, the sum, okay, was larger than this particular edge, direct edge. So therefore, length I was smaller than this. So this condition was not valid. For the other cases, this condition was valid. So in such case where this is valid, length I becomes this new length. And touch I
Veneer.
becomes veneer.
Excuse me, sir.
Yes.
Can you please go up to the graph? I wanted to ask something. Yes, sir. Sir, except for the direct edge from V1 to V3, there is no way we can reach V3 because V4 to V3 is directed backwards.
No, that is not the point. The point is that in this particular situation, should we include V2 or should we include V3? That was the question.
Yes, sir. Okay, sir.
And this is again trying to show that this guy veneer has entered into Y and therefore should not be considered anymore. Once again,
So what about the vertices which are already in Y? How do we keep track of them?
every time we are making length of veneer equals -1. So
But
those veneers will no longer be included in
length of I
the
for
computation.
if I is in Y, then length of I is here updated here. Oh, that will be -1. Okay, so that will be smaller.
That's
all
what I
over.
said.
Sir, the length veneer equal to -1 is included in for loop, right?
Which for loop?
The for I
It's
equal
included in the
to
repeat loop. It's included in the repeat loop, not in the for loop.
okay.
It cannot be included in the for loop.
Yes, sir.
Then to like the everything will be jeopardized.
Sir, if we do this, then how will we remember all the shortest paths, lengths from 1 to any vertex? If we update all to -1, then
Huh? No,
sir,
we are not updating all. We are taking length of, we are already constructing E here. Sorry, F here.
okay, so from that F we'll have to get it back.
Yeah, from F we will retrieve the shortest path. We don't need this anymore. Okay. So I wanted to quickly talk about a little bit on the knapsack problem. Deepank, are you here already?
Yes, sir.
Okay. So I'll give them a brief primer of the knapsack problem, and then you can take over.
Okay, sir.
So this knapsack problem asks you to imagine yourself as a thief. Okay. And suppose you have broken a gold store and you have a knapsack with you, which can carry some weight of gold. Okay. But then the knapsack can carry a maximum weight, say W. And if you put anything above W, the knapsack will break. Okay. So now your dilemma is to maximize. So, and the items you pick up from the store say bangles, necklace, ear pins, etc. All gold. Each of them have a value. Okay, this could be also like bars or ingots of gold. may not be jewelry, maybe bars or ingots of gold. Okay. Now they all have a value or price. Now your dilemma as a thief is to maximize the total value of the items that you steal okay, without breaking your sack. So if we try to formalize this problem, it turns out to be something like this. See, there are these items represented in a set. Say Wi is the weight of item I, and Pi is the profit or value of item I, and capital W is the maximum weight that the knapsack can hold. Okay. Now there is one more point, that in this case, if you take the item, you have to take the item in full, or you have to, or otherwise you have to discard it. There is no middle ground. Okay. So item have to be taken full, taken in full or none. Okay. So you cannot, break the item and take it. So these are gold ingots, say, or gold jewelry. You cannot break them and take it. Either you have to take them in full, or you do not take them at all. So this version of the problem is called the 0-1 knapsack. So either you take it or you don't. Now, what you want to do is the following. So suppose you are having to choose a subset A, okay, of S, fine, which will give you the max profit without breaking your knapsack. So this is what is exactly expressed by this particular problem. Okay. Now there could be a greedy strategy. Okay, you can think of a very simple greedy strategy. Okay, suppose I tell you that, okay, one greedy strategy could be take items of largest profit. This could be one greedy strategy. Okay. And then choose the next ones in the non-increasing order. What is the caveat? Where will this greedy strategy fail?
So when the weight of the item having largest profit is the largest.
So if the large profit items, okay, have very large weight, then this probably is not going to be a very good strategy. Let's see an example. Okay. Suppose you have 3 items. First one, say 25 pounds. And its profit is $10. And then there are the second and third, both of which are each 10 pounds. Okay. And their profits are $9 each. Fine. And your knapsack can hold a maximum of W, which is 30 pounds here. So if you go by the largest profit, then what will happen? You will earn
25 and it will
largest
earn only
profit
$10.
that you can earn is $10, right? And 25 pounds is gone in the sack. So you cannot take anything more. However, obviously, this is not the best strategy here. You can take the second and the third, giving you a total profit of $18, and the knapsack now has 20 pounds, which is lesser than W, well within the weight. Now, since you cannot, break this 10 pounds into 5 pounds or some other fractions, therefore, this strategy of taking the largest profit first does not work. Now, what about considering largest profit per unit? Suppose we have items like this. Say this is $50. Now let us find, in this case, the profit per unit. Okay, for item 1 What is the profit per unit? $50 by 5. That is $10. For item 2, $60 by $10. Sorry, by 10 LB. That is $6. And item 3 is $7. Now, if you ordered the items, then again, by the non-increasing order of profit, then say profit per unit in this case, then your greedy solution gives you, what should you take first?
Sir, $5.
$50 item.
Yeah, so this gives you $50. This is your greedy solution. Okay. Then next.
So 20 pound.
20. That gives you 140. Right? And then you have only 5 pounds left. Can you do anything with this? With this last
No,
5
sir.
pounds?
No, sir.
No. So this is the best profit that you can earn using a greedy approach. What is the optimal solution, by the way?
Sir, 20 pound and 10 pound.
You take the 10 pounds and then the 20 pounds. In this way, no space is wasted in the knapsack, and you also gain the maximum profit. Okay. However, now suppose I relax the condition. Okay. Now you can take fractional items. Then will the greedy approach work?
Yes, sir.
Yes.
So in fractional knapsack, this is called the fractional knapsack problem. Then how to solve the 0-1 knapsack to get the best solution? Acha, before that, tell me why this greedy solution is an optimal solution for the fractional knapsack.
So because we are utilizing the space for the best value.
It never wastes any space. How do we do this?
Using DP.
Very good. So we'll have to now frame out the optimal substructure. Let us say that A be the optimal subset of n items. Now there are two cases. Either A contains the item n or it does not. Now, if A does not contain item n, then what can we say? This helps us to build up the optimal substructure. If A is not containing the item n, so a particular item n is not there in A.
Then A is optimal for
A
all items
is
except n.
optimal subset of the first n-1 items. However, if A contains item n, then what?
Sir, A is optimal for n items.
Nah. Is if A contains item n, then the total profit
Equals to profit for n minus 1
total profit
plus profit for n minus 1 plus profit of n.
Total profit is equal to Pn, which is the profit for item n plus the optimal profit obtained when the items were chosen from the first n-1 items. That's all. Pn plus the optimal profit from the previous n-1 items.
W minus Wn.
Very good. So there is this constraint. Under the constraint, that the total weight cannot exceed how much? When can you add item N?
Capital W
Capital W
minus WN.
The total weight cannot exceed this much. So let's say for I greater than 0 and W greater than 0, PIW be the optimal profit obtained when choosing items only from the first I items under the restriction that the total weight cannot exceed W. Then PIW can be expressed as maximum of P I minus 1 W, that is the previous one, or the profit that comes from I plus P I minus 1.
W
What
minus
here?
W.
W minus WI because whenever you add WI, this has to remain under W. Otherwise, it remains as it was earlier. And the maximum profit is obtained in which cell?
P and W.
So you see, a single problem with two different versions have two different approaches. Okay, this is why we learn different paradigms of algorithms. Okay? So while one paradigm was useful in solving the fractional knapsack, the other paradigm was useful in solving the 0-1 knapsack. So the optimal solutions can be obtained in the two different problem setup using two different algorithmic paradigms. That's why this motivates us to learn the different paradigms of algorithms. We started off with a very simple example long back. That was the Fibonacci series, where we motivated ourselves that recursive approach is probably, or a divide and conquer approach is probably not a good one, and a DP is a better solution. Similarly, in some cases, a greedy approach is a better solution, whereas in some other cases, a DP approach is a better solution.
Sir, sir, can we solve the fractional knapsack problem using DP?
Very good. Take it as a homework. as long as you can find the optimal substructure. Try this. Both these problems. Okay, at this point, like, over to Deepak.
Okay, sir.
Sir,
हाँ
sir,
हाँ
sir, how to find the complexity of time complexity of a function which uses the random number generator?
So, which a function which uses random number generator. Okay, so if time permits, any one of us, either myself or Pawan, will teach you randomized quicksort. And here we will explicitly show you how to do this. Okay, this is typically this will boil down to an average case that I had taught you in the very beginning. Unless and until there is any distribution assumed on the input, it will boil down to an average case analysis. Yeah, so Deepak, I'll have to make you the presenter. There are so few students in the class.
Sir, it was above, sir.
So you missed me. Yeah, you missed me, sir.
Okay, I'm still searching. Okay, yes.
Yeah.
You should have the ability to present now. Let me unshare my screen. Recording is on. You should be able to share your screen. Yes, your screen is visible.
Hello. Am I audible?
Yes, you are.
Okay. So let's start the tutorial number 9, greedy on graph. Okay. Yeah. So we will cover these things like I will list some of the important greedy algorithms which are in the case of graphs. Okay. And then we will solve a previous year labs assignment question. Okay. And I have a small demo of Jack's algorithm working in the real life application. So that is very interesting. So please stick up to that point at least. And at, at the last, we will, if the time permits, then we will solve a few extra problems. Okay. So let's start with, okay. So these are a few important greedy algorithms that you must have like which sir must have taught you in the class. Okay, this one, and this one. Okay, like JAXA used for shortest path search from a particular node. Prims and Kruskal are used to find the minimum spanning tree. Okay, and then there is one more algorithm. I don't think this is covered in the class. Okay, but there is a case when Dijkstra fails. Okay, which is the case of negative weight cycle. Okay, in that case, like we generally use Bellman-Ford algorithm. I don't think this was covered in the class, but you can always find reading materials online. Okay. The main focus of this tutorial will be Dijkstra shortest path. Okay, and there will be a few problems at the end, which might involve MSTs. All right. So let's move on to the previous year lab assignment problem. Okay, so this is the problem statement. So what we are given here is like consider an into n grid of squares or blocks. Okay, like you all know grids, right? Okay, so we are given this n into n. Okay, with coordinates ranging from 0, 0 to n minus 1, n minus 1. Okay, each value of the grid, each value represents the elevation at that particular block. Okay, elevation at that particular block ij. Okay, when you start to move at time t is equals to 0, like you will be at this particular start point 0, 0, and you will start moving from there at t is equals to 0. Okay, since the blocks have elevation, sub elevation. Okay, so as the time progress, the blocks rise such that at time t, the elevation of ij block will be this max of ij t. Okay, you can only move to your adjacent blocks, top, bottom, left or right. Okay, I will come to this in a second. Okay, and only if and only if the elevation of the both the blocks individually are at most t. Okay, so suppose like these are two adjacent blocks. Okay, this has a height of elevation of 3 and this has a elevation of 5. Okay, so you can move from this block to this block. Okay, only at t is equals to 5. Is that clear? Because at t is equals to 5, the height of this block will become 5. Okay, then you can directly move to the next block. Okay, and the other thing is that you can move infinite distance. You can move infinite distance in 0 time. Okay, this is just for our facilitation that when we are at a particular cell, okay, we don't need to care about time. We can just wait at that, and when t is 5, okay, then when t is equals to 5, then we can simply move to this particular cell. Okay, and the time will still be t is equals to 5. Okay, and yeah, okay. So this was the problem statement. Is the problem statement clear to everyone?
So can you explain once again when can we move to the adjacent blocks?
Yeah, sure. Okay. Yeah, so consider that you are at this particular block, which has an elevation of 3. Okay, and the adjacent block is this one, which has an elevation of 5. Okay, then here it says that you can move to your adjacent block if and only if the elevation of both the blocks is at most t. Okay, okay. that means, and when it's t, okay, when the time is t, then the elevation of the blocks will be this maximum of grid ijt, right?
Yes, sir.
Yeah. So when time is t is equals to 5, okay, then the elevation of this block will be 5, okay, and the elevation of this block will still be 5 because max of 5 comma 5 is 5, okay. So you can easily move to the next block at t is equals to 5, right?
Yes, sir.
And since you can move infinite distance in 0 time, that means like when you move to this particular block, the time will still be t is equals to 5. Okay, that means suppose there was a next block, okay, which has an elevation of 4. Okay, so at t is equals to 5, this particular block will also have elevation of 5, right?
Yes, sir.
Yeah. So at t is equals to 5, you can directly move from 3 to 5, 3 to 4. Okay. You can directly move from here to here at t is equals to 5.
Okay.
Okay. But the constraint is that you must stay within the boundaries of the grid. Okay. That is from this part. Oh, sorry. Yeah. That is from this particular cell. You cannot move in this direction or in this direction. Okay.
Sir,
Yes.
is given
Yes,
that we
sir.
move only to adjacent blocks, so can we directly go from 3 to 4, even though the heights will be 5 at equal?
No, you can directly, I mean like step by step, like you will go from 3 to 5, then you can go from 5 you will go to 4. Okay. But this whole process can happen at t is equals to 5. Okay. Because you can move infinite distance in 0 time.
Okay.
Okay. Is it now clear to everyone?
Yes,
So
sir.
what do you have to find out? I mean, what is the
Yeah.
command of the program?
Yeah, I will come to that
Sir,
in a second. Yes.
sir, is it true that after a certain point of time, all the grids will be at same elevation? Like they all will the
Yes.
following t?
Yes. Like suppose like the value, that is a very good point actually. Like suppose the grid values are like this, okay, 100, then this is 5, 6 and something, okay. The thing is that the maximum value in this whole grid is 100, okay. Then at t greater than equals to 100, all the blocks will have an elevation of t, okay. So you are free to like, then you can freely move from any particular cell to any cell, right?
Yes,
In
sir.
0 time. Yeah. Okay. So let's like uh, model this problem as a graph problem. Okay. So suppose like you have this cell and the cell is I comma j. Okay. And it is said that you can move to the adjacent cells, that is in these 4 directions only. Okay. So the coordinate for this particular cell will be uh, I comma j plus 1, right? And for this will be I comma j minus 1.
Sir,
And this, yes.
sir, in previous you said that we can move infinite distance in no time. So can we move horizontal and vertical in same time, or we shall go only horizontal or only vertical?
You have to like from one cell, you can move to the adjacent cell only. Okay. But from when you are at the adjacent cell, then you can move to another adjacent cell, which is in the vertical direction. Okay. And you can move like, so you can cover this whole distance in 0 time.
Can't we come back to previous cell?
Of course you can, like when you are at this particular cell, okay, then you can come back to this cell and then go back to this cell. Okay.
And
I'm
time
just, yeah. again the time will be 0 because you can move infinite distance in 0 time. Okay, I'm just I'm just making the plot of the problem here. Okay, like we will come to the questions like what is asked to us later. Okay, just make sure that you get the problem theme correctly. Okay, so from I comma j you can move to I comma j plus 1, j minus 1, I minus 1 j, and I plus 1 j, right? Only these four particular cells. And of course, like if this cells are inside the grid, right? Okay, so you can consider a particular block as a node in a graph. Okay, and then connect it using edge to its adjacent cells, right? Is this clear? Like how to like project it as a graph problem? Okay.
Yes, sir.
Okay. Now that you have the understanding of like what is the plot of the question, these are a few things that is asked to you. Okay, suppose that you are standing at an initial node sx comma sy. This can be any node in the grid. Okay, so this can be any node in this particular grid, any node. Okay, and you are asked that what is the least time in which you can reach the fx block. Okay, so you are given two coordinates. One is sx sy and other is fx fy. Okay, you have to follow some path and get from source to the final point. Okay, and find out the least time in which you can reach this particular block. Okay, and other things like print the path and print the number of blocks traversed are easy to find once you have found the path from uh, sxy to fxy, right? Just a second. Yeah, okay. And like there are many ways to solve this problem, but you have to use the Dijkstra shortest path algorithm to solve the problem. Okay. Let's try this on a working example, like how this will work. Okay. So this is n, that is the grid is of size 5 into 5. Okay. And this is your grid. This is given as S and this is given as F. All right. So that means your start point is this and your ending point is this, right? Just yes. Okay.
Sir?
Yes.
Sir, how is the ending point is 6?
Because it is 4, 4, right? 0, then 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. The grid is 0 indexed.
Okay, sir.
Okay. And the coordinates that you are given are also 0 indexed. So that is 0, 0 is this particular point. Okay. Yeah. So at t is equals to 0, you are at 0, 0. Okay. Then from here you can move to either 0, 1 or 1 0, right? Because you cannot move in other directions because they are outside the grid's boundary, right? Okay. Now the elevation of 0 comma 1 is 1. 0 comma elevation of 0 comma 1 is 1. Okay. And elevation of 1 comma 0 is 24. Okay. So when can you move from 0 to 1?
When time is equal to 1.
Time equal to.
Yeah, right. So when t is equals to 1, we can go from 0 comma 0 to 0 comma 1, and at t is equals to 24 we will be able to go from 0 comma 0 to 1 comma 0, right? Okay, let's try to find out an optimal solution for this, like what will be the least time to reach from 0 comma 0 to 4 comma 4. Okay, so obviously like I'm not proposing any algorithm right now. I'm just showing this how we can reach there. Okay, so at t is equals to 1, we can get to 0 comma 1. Okay, then when can we move from 1 to 2? At t is equals to 2?
Yeah.
Yeah, right. Okay, and similarly from 2 to 3 at t is equals to 3, and yeah, and then t is equals to 4. Then from here to here t is equals to 5. Okay, and then if you want to move in this direction, then it will take t is equals to 21, and if you want to move in this direction, it will be t is equals to 16. Okay, so let's move to 16. Okay, then we can from 16 we can go
We can go directly without any time consumption, because
yes,
15, 14, 13, 12, 11, it will take the step.
yeah, just I'm mentioning that you can move to t is equal to 20th in t is equals to 20. Okay, but in this direction you can directly move at t is equals to 16, because the elevation of both the blocks is at max 16, right? So at t is equals to 16 you can directly move in this direction, keep moving. You cannot move here at t is equals to 16. That will take at least t is equals to 17, right? Let's move over here. Then we can move here, here, and we have finally reached 6, right? Yeah, okay. So to reach 4 comma 4, we can reach there at t is equals to 16, right? Yeah, and following this particular path, uh, this. Okay, so we have the path also. Okay, and pin the path travel to reach fxy. So we have the path, so we can directly print 0 0 0 1 and all. Okay, and we can easily count the number of blocks, which will be 5 5 5 into 17, right? Okay, so the path will have 17 blocks, and we will take at least t is equals to 16 time to reach 4 comma 4. You can see that there is no other solution, like there is no other way you can reach in less time to t is equals to to 4 comma 4, right? Okay, is the problem clear now to everyone? Like we have not proposed any algorithm yet, right? Okay.
Yes, sir.
So let's now think about approach, like how can you solve this particular problem? Okay, using Dijkstra approach, using Dijkstra shortest path algorithm. I hope you all remember Dijkstra, right? Okay. So you can have 2-3 minutes to think of a solution. Okay. Then we will discuss the approach. Okay. Meanwhile, if you have a doubt, you can ask me. Okay. So let's go over the hints while you are thinking. Okay. So like the first question that you should ask is that how is it analogous to JAXA shortest path search case, right? Anyone?
Instead of length, we need to check for time.
Yeah, right. The thing is that in both the cases, we have to start from some node and reach a final node, and we have to minimize some cost. And in JAXA, it is the length of the edge, but here it is the time. Okay, right. Okay, now suppose that V is a neighbor of U. Okay, and you already know that how much time you are gonna take to reach V. Okay, and can you use this particular information, okay, to reach node U via V? Like, can you like calculate the time it will take if you move from V to U? If you already know that how much time it takes to reach to U to V, sorry.
Elevation of U minus elevation of V plus time required to reach V.
Come again?
Means time required to reach V plus elevation of U minus elevation of V.
Elevation of U minus elevation of V. Okay, and these are at time t is equals to TV or at time t is equals to 0, like the initial elevation that was given.
Means it is time required to reach U.
Yes, you are. But the elevation is at t is equals to V, right?
Yeah, no, initial.
Okay, at t is equals to 0 that you were given. That is grid of U and grid of V value, right?
Yes. Means it will only work if elevation of U is greater than elevation of V.
Will this work actually?
Shouldn't we see the elevation at time V instead?
Yeah, I guess. Like you guys have to think of an approach. So you guys tell me. Do you think that this will work? Like if you want to revisit to the problem here. Okay, so here, suppose we are moving from 5 to 16. So you are saying 5 plus 16 minus 5, right? Okay. Yeah. So it's correct here. But suppose you're moving from 7 to 6. Time
So
here is 16. So 16 plus 6 minus 7. It does not work here, I guess.
So, but elevation would be max of time and grid elevation initially. So both would have become 16, right? So at 7 to 6.
Yes.
Put it with max of TV.
Yes, right. This should be max of TV, comma
Initial elevation.
initial elevation of U, right?
Yes, sir.
Okay, yeah. So this will be the time taken to reach you if you are moving V to U, right?
Yes,
Good.
sir.
Yep. This is the right equation. Yeah. Elevation of U or time taken to reach V, whichever is maximum. Okay. So now, now that you know that if you already know how much time you are gonna take to reach V, and you also know that how much time you will reach U via V. Okay. So can you use this particular thing? Okay. Like, oh, you know, right? When we are on the update step of Dijkstra algorithm, okay. Uh, like we are also moving from some visited node U, okay, to its neighbor node V. Okay, we want to update the distance for V. Okay, so how can you use this thing here? Okay.
If the previous distance for V which was stored was greater than the new distance to V which we found, then we'll update it.
Yes. Is everyone did everyone understood what it said?
Yes, sir.
Okay.
If you can repeat again.
Yeah. Okay. So he said that suppose we know the distance, we know the previous distance to reach V is dsv. Okay. And just now we calculated that if we know that we can reach U, okay, in some time, say that is dsu, okay, and we want to reach the node V, okay, so we can simply take the maximum of these two, like, and update this with this, right?
Okay, sir. Thank
Yes. Great. Okay. So let me explain it a bit better. Okay. So this is the source node S, and this is the node U. This is the node U, which we just got in the visited set of Dijkstra. Okay. And this is node V. All right. Yep. I think I've used all the colors. Okay. Yeah. So we already know that to reach U via S, it is d S to U. Okay. And to reach U, sorry, just a minute. Yeah. To reach V, it is dsv. Okay. Now we want to reach V, like we want to find out the optimal time to reach V. Okay. Since U is a neighbor, like say U is a neighbor. Okay. And we have put it in the visited set. Okay. That means we already know the optimal time taken to reach U, right? Okay. So for V, we can update it as the time taken to reach V via U will be maximum of DSU, comma, the elevation at V, okay, which will be grid V, okay, and if the condition will be if the previous distance that we know is greater than ds u to v. Okay, then we can update. Okay, and one more thing, like since we were also asked about the path, okay, so we all know that like to get back the path we need to store the parent. Okay, so we can also store the parent of v as u. Okay, is the solution approach clear? Like this is the main part of Dijkstra, right? Like you just got a particular node into the visited set and now you want to update the distances for its neighbors, right? So that is the only part that you need to think in Dijkstra, right? Okay, so this will be the update step of Dijkstra. Okay. Now let's rework the example using Dijkstra, right? So this is same as the initial input that we had. Okay, so this is the yeah. So this is S and this is F. We from here to here. Okay. So initially the visited set. Let's make the visited set as yeah, visited set as set, which is empty. Okay, and initially we know the source is 0, 0. Okay, so distance 0 to 0 is 0. Okay, so at t is equals to 0, this will be the first element to come out of the to come into the visited set. Okay, so at t is equals to 0, we have 0, 0, and its neighbors are 0, 1 and 1, 0. Okay, so according to the update step here, okay, what and initially all the other distances are infinity of obviously, right? Okay, so for 0, 1, how do we update? So the max will be max of 0, 1. Okay, so it will be a value of 1, and for this particular we have maximum of 0, 24, which will be 24. Okay, that means that if like the time taken to reach 0 is optimal, okay, then through 0 we can reach 1 at t is equals to 1, and we can reach 24 at t is equals to 24. Okay, so this will be d of 1, 0, 1, and this will be d of 1, 0. Okay, so now which next element should come into the visited set? And these of course will be yeah. So can anyone tell me like which will be the next element to come into the visited set now?
0, 2.
So D01.
0, 1, right? The guy who said 0, 2, did he understand like why 0, 1 will be come now in the visited set?
Yes, sir.
Okay. So at t is equals to 1, the set looks like we have 0, 0 and we have 0, 1. Okay. Now we update the neighbors of 0, 1. Dijkstra says the unvisited neighbors of 0, 1. Okay, since 0, 0 is already visited, so we will focus on 0, 2 and 1, 1, right? So similarly, we can update 2 here and 23 here, right? And then this 0, 2 will come out to the visited set. Okay, and similarly we will move from here to here to here to here and then to here. Like when we are at 4, there is only one unvisited neighbor of 4, that is 5, right? Okay, and now when we are at 5, okay, so the visited set looks like everything, and this 1, 4, right? Okay, and now we can move either in this particular direction 21, or we can move here or here. Okay, let's update it. 1, 4, which will move to 1, 3, or 2, 4, right? So here, like we already know that now the distance to reach 21 is 21, right? Because when 3 came into the visited set, it did update the time to reach 21, right? Okay, so to reach 21, we need at least t is equals to 21. Okay, and according to 5, okay, it says that it should be 21 only. Yes, okay. So we won't update because 21 is not greater than 21. Okay, and here we update it as 16. Okay, so now 16 will come out because for all these nodes, the time is 24, 23, 22, 21, and 16, right? So 16 is the next nearest node. Okay, so 16 comes out into the visited set. Okay, now from 16, either we can go to 20 or we can go to 15. Okay, either here or here. Okay, so for 15, how we will update, like same max function of 16, 15. Okay, the time taken to reach 16 is 16 and grid value is 15 here. Okay, so max is 16. Okay, so again, like in the in the unvisited set, we have 24, 23, 22, 21, and 50 and 16. Still 16. Okay, so we again keep moving in this direction. Okay, and similar. Do you have a question?
Sir, at each time we will check for each visited node, right? For 0, 1, 2, 3, 4.
Yes. Not again, because those are already visited. Okay, and the most important thing of Dijkstra is that once you have visited a node, okay, it says that you have reached the optimal distance for, or you have calculated the optimal distance for that particular node. Okay, you do know, like you are understanding the difference between visiting a node and updating its value, right? Like
Yes.
we visit that when we say that we are visiting a node, okay, it means that that is a particular node which has the lowest value of distance, that is it is nearest to the visited set. Okay, because initially all the distances were infinite, only the distance of 0 was 0. Okay, so from all these cells, okay, 0 was the closest cell, so we took out 0. Then 0 updated the distance for its neighbors, 0, 1, and 1, 0. Then the distance set looks like for 0 it was 0, for 1 it's 1, for infinite, and then for 24 it is 24, then infinite, infinite. Okay, so now since 0 is already visited, okay, now it's turned for 1, right? So 1 comes into the visited set. Okay, and then we update the distance for its neighbors. Okay, so we updated the distance for its neighbor, and now there will be 2 instead of infinite, and there will be 23 instead of infinite. Okay, Since 0 and 1 are already visited, then 2 is the nearest node. We take out 2. Is it clear? Like, what is the meaning of visited in Dijkstra? Like, this is okay. Do you have another question?
Yes, sir. Here we reached 5 in this process. We reached 5.
Okay. Yes.
And in place of 21 and 16, we have some 30 and 35, something like that.
Okay.
Then from 5 we cannot move till till the time is 30.
Right.
So directly go from 3 to 2 to 22, and we can find the way.
Yes. Right.
So isn't it
You are right.
necessary to check for all previously visited neighbors and to its and then neighbors?
Okay. I think yeah, I think your doubt is okay. Suppose we are at node this, okay, 5. Okay, let's see the distance set. Distance set D. Okay, what it will be? Like it will be 0 for 0, then 1, then 2, 3, 4, right? And then for 24, it will be 24, 23, 22, then 21, 5, right? Up to this, it is clear, right? Because there is no other node right now. Okay.
So can you write it like the matrix that we have?
Okay. Okay. 0, 1, 2. We have only explored up to this particular point, out of which this node, this are visited, and we are at 5. Okay.
Sir, is 24 visited or not? Like we are at
No.
0.
No. When we were at 0, okay, we updated the distance of 24. Okay, from infinite to 24. Okay, but it is not visited yet. Okay, because we
Yes.
always visit the node which has the minimum distance. Okay, so when we updated, when we visited 0 and updated for 24 and 1, 1 has the minimum distance. So 1 will be visited next, right? And then from when we visited 1, we updated a distance for 23 and 2. 2 has the minimum distance, so 2 pops out. Like 2 has the minimum distance among 2, 24, 23, and infinite. Okay, so 2 pops out. We update the distance for 22 and 3. 3 now has the minimum distance, it pops out. Okay, suppose a node here, suppose, let me change it a bit. Suppose here the value was 27. Okay, and the value here is 30. Okay, so now when we reach 5, okay, we update the distance for these nodes 27 and 30, which will be 27 and 30 only. Okay, but when we take out the next node, which will be the next node that comes out, that which will be the next node we visit? Currently in the 22, right? Because in the distance set we have 22, 23, 24, 27, 30, and others are infinity, right? Okay, this is the unvisited set. Okay, and the visited set comprises of 0, 1, 2, 3, 4, and 5. Okay, so we will take 22 from here and put it in here, right? Because it is the closest. Okay, and when we take 22 out, since 2 is already visited, okay, so we update the distance for this, and for the node below it, right? Is this clear?
Yes.
So it sets the matrix for the minimum value again.
Again?
Yes, sir. In the unvisited matrix, in the matrix we mark the unvisited ones, right?
Yes.
So we again search in the matrix for the minimum value.
Yes.
Okay.
It is like you can imagine as a simple array because you don't need the spatial information, right? You only need the values and the associated cell. Like the 22 is at 1,2. Okay, so 1,2 is the next cell that should be in the visited set, right? I'm explaining in terms of value because all the values are here distinct and it's easier to understand. But you do understand that we are like doing this for the cell. Okay, like 22 is the cell 1,2. Okay, so 1,2 comes out and its neighbors are 1, 3 and 1, 1 and 2, 3. Okay, because this 0, 2 is already visited. Okay, so we update the value for these particular cells. Is it clear?
Yes, sir.
Okay. If anyone has a doubt, please ask. And in this way, we can then move from 11 to 10. Then we move from 10 to 9, 8, 7, and 6. Because all these values, all the other values, this, all are bigger values. All right, then 16. Okay, so they never pops out. Okay. Before they pop out, the other cells get into the visited set. Okay, and we reach the final hour cell 4,4. Right, and at that point when we visit, mark my word, when we visit 6, we know that we have reached the optimal solution. Someone has a question in chat, just a minute. We can move only adjacent moves, so how 22 after 5? Yeah, right. You can move adjacent cell, but we are not moving, right? Okay, over here, right? Okay, so the thing is, what will happen is, okay, suppose our final cell was this here, which is say 25. Okay, just the cell below 22. Okay, so here we updated the parent of 22 as 2, and here we will update the parent of 25 as something. So suppose say 22 only. Okay, like all these values are bigger, 30 or 35. Okay, so there is only one possible way to reach 25. Okay, so when we retract the path will be 25, then 22, then 2, then 1, then 0. Okay. This is on this path, we are moving in adjacent cells only, right? Saurabh? Hello. Right, Saurabh? Like we are actually, when we take out 22, we are not moving from 5 to 22. Okay. Do not mix graph traversal and Dijkstra. Okay. Do not mix graph traversal and Dijkstra. Dijkstra just greedily updates the distances for the nodes. Okay, but for graph traversal, you'll need DFS and BFS. So if you were to apply DFS and BFS, then you can only, from 5, you can only move to 27 or 30 here. Okay, but we are not using a graph traversal algorithm here. Okay, we're just updating the weights, or we are updating the distance. Is the solution clear to everyone? Like, if you still have a doubt, you can ask. After this tutorial, you should really go back and thoroughly read the Dijkstra algorithm, okay, and understand the meaning of visit, okay, because this term is really confusing, okay. This term is really confusing, and remember one thing that I will list it here. When we visit a node in Dijkstra, okay, node U say, okay, when we visit a node U in Dijkstra, we have the optimal to U, okay. Remember this particular point by heart. Like, this is a very strong argument of Dijkstra. Okay, like whenever you put a node in the visited set, okay, you have the optimal path to that particular node. Okay, so remember this particular point. And if you don't know the proof of Dijkstra, I will say that you should at least go through it once, because it will really help when when some variation of Dijkstra comes in. Okay, so okay, because rarely you will get a question that does the straightforward application of Dijkstra. Mostly you will have to think about the update step. Okay, like what will be the condition and update, write the code. Okay, so if you don't have the understanding of like what are the strong arguments in Dijkstra, then it might become a bit difficult. Okay, so understand this particular word very clearly. What is the meaning of visiting a node in Dijkstra? Okay, I hope like the solution approach was clear. Let's look at the implementation. I think this will make it a bit more clear. Okay, so let's move step by step. Okay, so the first thing is that how do we represent a cell? Okay, so to represent a cell, I guess you all know that we can use a structure, row call. Okay, and then we were also told that if we are like we cannot move beyond the grid. Okay, so if we are at the edge of a grid, okay, of the grid, we can only move in this and in this direction. Okay, so to check that whether like the new cell is within the boundaries, we need this particular function. Okay, and then this is a new array to navigate the neighbors. I have put this particular array as a highlighted here because I have noticed that whenever there is a grid type of question where you have to do traversals, okay, most of the students write 4 if conditions. I hope like I know like many of you do write 4 if conditions, like we are at I comma j now, and we can move to I plus 1j, I minus 1 j, ij minus 1, ij plus 1. Okay, so students tend to write 4 if conditions, check this thing 4 times, and then do the DFS in all those 4 if conditions. Okay, so this is a better elegant approach to do this. I will show how to. Okay, you can clearly say see that suppose we are at ij. Okay, so using minus 1 comma 0. Okay, so using minus 1 comma 0, we can reach over here I minus 1 j. Okay, using 0 minus 1, we can reach over here. And similarly for others, for this, we can reach over here, right? And from here, we can reach over here. Okay. Any doubt up to here? I think we are running out of time. Okay, so this is the main loop of Dijkstra. Okay, I think I have missed one thing here. Okay, that there will be a loop from loop for I. I 1 to n and loop of I hope like the basic implementation of Dijkstra was covered in the class, right? Yeah. Okay, so this is the particular loop where we are finding the next candidate node. Next nearest node to put in the visited set. Okay, so here we can say that C visited node. Okay, in this particular step of Dijkstra. Okay, C is the nearest node which has the minimum distance. Here the distance is in terms of time. Okay, so this is nothing but we have an array of time. Okay, and we are just calculating which particular cell has the minimum time. Okay, so it happens out that C has the minimum time. Okay, so we mark C as visited. Okay, it is clear up to this point, right?
Yes, sir.
Okay, and over here, we are updating the neighbors of C, Okay, so what I have done over here is that the K goes from 0, 1, 2, and 3. Okay, and I have used this here, this particular array. Okay, so this is 0, 1, 2, and 3. Okay, so suppose C dot row is I and C dot call is J. So we can easily see that V row and V call will be one of these, right?
Yes, sir.
Okay, then we have to check for the validity whether the cell is inside the grid or not. Okay, and we also need to check if the this particular cell is already visited. Okay, uh, like over here, like when we are suppose at 3. Okay, so we don't want to update the distance for 2, right? Because 2 is already in the visited set. Okay. Okay, 2 is already in the visited set. Okay, and then it's continue, and then this is a simple update condition that we just saw. Like this is the grid value for V. Okay, and here we check that we are basically taking out max here. Okay, maximum of TC, comma grid V. Okay, just the way I told. Okay, and then we are comparing it to the already known time for V. Okay, and if it is optimal, then we update, and we also update the parent, right? Is this particular code clear to everyone? Like this is exactly what we discussed. Like all the up to here, like I think up to here is generic Dijkstra. Okay, only over this particular small section, like the if condition. Okay, uh, we have to just customize this particular part, the if condition of Dijkstra. How do we update the distance for neighbor, right? I
Yes,
hope
sir.
I hope this is clear and everyone is still listening. Okay, we are almost done. Okay, so don't get bored. Uh, Here we can see that for everything we are using a 2D array. Like for visited we have 2D array. For time we have 2D array. Okay, for everything we have a 2D array. Okay, but you can do it in do it using a 1D array only. Okay, let me show you how. Okay, so the size of grid is n into n. Okay, that is there are n square cells. Okay, suppose we have a cell 3,5. All right, and n is 7. Okay, so what I am doing is basically like we have a 2D representation. I want to translate it into a 1D representation. All right. Okay. So if we have three, you want to say something?
So isn't this the basic how the 2D array gets stored if we
Uh,
initially
Not always, actually. Not always.
if we dynamically allocate, then it won't. But in general, if we initialize, then it will be the same way.
Yeah, again, I'm saying like it may happen that suppose you first allocated the pointers and pointers, okay, and then for each of the pointers you did separate allocations of n, 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 n. Okay, so it is not, yeah, so it's not necessary that all the uh, n arrays of will be contiguous, right? And one more thing for the C++ guys who are familiar with STL, if you are using vector, okay, then like also like this happens, right? The all the cells are not contiguous in memory, right? Uh, Here efficiency is actually related to related to cache hit miss case, which you will learn in your third year. Okay, but this is an interesting approach which might be helpful to you somewhere else, because this particular approach sometimes make the what do you say makes your implementation very clear. Okay, so we can represent 3 comma 5 as 21 plus 5, 26. Okay, and we can represent 0 0 as 0 similarly, and say if we have 26, we have to map it back to 3 comma 5. Okay, so we do is we first divide it by 7, which is n, and then take modulo with 7. So you can say that this is 3. This is the integer division. So we get 3 and 5. Okay, and these all are O1 operations, right? So you are not increasing the complexity of the approach. Okay, so uh, is this transformation clear to everyone? Like how we can transform a cell I comma j to a number on a number line, and then a number on number line to a cell, right? Is
Yes,
it
sir.
clear?
But
Okay.
sir, still it will be only order of n square. No?
Yeah. I'm just saying that this makes the approach very clear. Like compare this particular implementation with this implementation. Okay, like you will get the code for both the implementations. So you can compare like which particular thing you feels is more clear. All right. because here you can see that you are directly updating parent of VSC. Okay, here you are directly taking the max value. The code becomes a bit clear. Time of C. Okay. All right, and here like we are transforming back to get the neighbor, check its validity. Yeah, and one downside of this approach is that you cannot directly check the validity in the number line. Okay, you have to first map it back to 3,5, check validity of 3,5, and then get it back. Okay, so here, like first I got the I, j, checked its validity, and then got the uh, number representation on the number line. All right. Is this approach also clear to everyone?
Yes, sir.
Okay. Yeah, so the implementations are available at these particular links. Okay, so you can go through them and look at your leisure time. Okay, and I have also included a STL implementation of C using C++ implementation using STL. Okay, so if someone is interested, then they can have a look. All right. Now let's move to a small demo of
Few test cases.
yeah.
Can you give us few test cases for us to verify after completing this?
Yeah, sure. Like the implementation, just a minute. Yeah, the implementation has test cases at the last. Okay.
Okay, sir.
So there are two test cases, one that is in the presentation, okay, and one in the links. All right.
Okay, sir.
Yeah, just a minute. Yeah, okay. The implementation have okay. Uh, does someone have a question up to this particular point? Like that ends our previous year lab assignment. I think we are yeah, it's 1:30 already. Let's wrap it quickly. Okay. So let's have a look at a very small video clip. Okay. Okay, so let me explain the scenario here. Okay, as you can see that there is a green circle and a red circle. Okay, and then there is a, if you can see that blue rectangle over there, right? And then some white shapes. Okay, so the scenario is that there is a car which is represented by a blue rectangle. It has to start from the green point and reach the red point. Okay. Also, it has to avoid these white obstacles which are in the path. Okay. Okay. And it has also, it should also reach there with the least distance. Okay. Like if you have used Google Maps or any map, okay, then you know that whenever you calculate a distance, sorry, whenever you want to know the distance, it considers some factors and tells you the minimum distance or minimum ETA distance, right? Minimum distance, minimum ETA path actually. Okay, so actually like in those particular scenarios, shortest path algorithms can be used. Okay, so of course, like some complex versions of Dijkstra like A star can be used. Okay, but this particular demo has been made using Dijkstra only. Okay, so have a look. Okay, you can see that the car is not colliding with any of the obstacles and trying to take the shortest path from green to the red, right? Like there are few more things to notice that first thing that the car is not I think that will be too much. you're getting like how Dijkstra is used in path planning and all, right?
Yes, yeah. Like it is trying to go the shortest path, but then it also tries to avoid the places it should not go.
Yes, yes, right, right. Basically, the thing is that you can simply mark those particular cells as obstacles. Okay, so when you are updating the distance, you can just ignore those particular cells. Okay, you can just ignore the white cells, and it won't calculate a path like intersecting the obstacles. Okay.
Just a doubt.
Yeah.
Like this whole map is like a kind of pixel matrix.
Yeah, it is a bitmap actually 0 and 255.
Okay, okay.
And there is a green circle and a red circle.
Okay, got it.
Yeah, this is a pixel map, right? Of course, like for visualization, we are using some libraries, but at the core of this algorithm, there is Dijkstra. Okay, so if someone wants to have a look at like how the code looks or something, you can like contact me later on Teams. Okay. Yeah, so there are extra problems which I wanted to go through. Okay, but I think we don't have much time left. Okay, so like I have included the problems and hints. Okay, and I've also included the link to the question where you can submit after you have solved them. Okay, so if you want to submit the questions, you can go to the link and do the submissions. Okay, and here are some few more questions like after you are done with these basic questions. This particular question, Jack goes to Rapture, is similar to the last year assignment that we just discussed. Okay, so if someone wants to implement and submit like and think again, okay, so they can head over to this particular question and solve. Okay, and there are a few particular like there are few difficult questions here like the shortest path code forces. Okay, and for this I will suggest that first you get understanding of Dijkstra like the proof and the arguments. Okay, then I think you will be able to solve this. Like there is nothing like it is not too hard. Okay, and then there is one more thing like I don't think uh, 01 BFS is covered in the class, is it? 01 BFS?
01 knapsack was covered.
Yeah, 01 knapsack is covered, but 01 BFS is not covered, right?
No, sir.
Yes, 01 BFS is actually a very good algorithm to find the shortest path. Okay, but it only like it we can only use it in some special cases. Okay, which is this particular question. Okay, I have included the hint too, so you can read the question, solve using Dijkstra. Okay, then use the hints and try to solve it using 01 VFS. Okay, the uh, the thing why I'm advocating about 01 BFS is that in some special cases, 01 BFS is very efficient as compared to Dijkstra. Okay, because you all know that Dijkstra's complexity is E log V. Okay, but for 01 BFS, the complexity is only log E plus V. That is simple BFS traversal, right? Okay, so sometimes you can have a question where the time complexity bound is so strict that you cannot use Dijkstra. Okay, but it somehow boils down to 01 BFS. Okay, so it is a very beautiful concept, and I think like you should know this. You all should know this. Okay, so I have included a link here. Read here, so you can read like how to do questions or like what is a 01 BFS concept. Okay. So if you have any doubts, then Chirag, you want to say something?
No, sir.
Okay. So if you have any further doubts, I think the class time is over. you can directly reach to me on Teams. All right.
Yes, sir.
Okay, and I will put up this slide, and all the links to the submissions are to the codes are already in the slide. Okay, so you can after the class look at the slide or the code if you want to. Okay.
Thank you, sir.
Yeah. Okay.
Thank you, sir.
So yeah,
Thank
this
you.
class is dismissed. You can leave now. If you have a doubt, you can ask or you can leave.
Thank you, sir.
Yeah.
Thank you, sir.
The demo video is also in the slide, so if you want to look at that, you're free to look.